Human beings love symmetry. It's everywhere in our art and in our architecture and design. And mathematics, I hope to show you today, is the language best used to describe that symmetry. So I just want to begin with a couple of examples. The picture that's on the title slide here is a picture of a design that's in the Grand Mosque in Paris, and it's got this lovely radial symmetry with the pattern repeating itself around the circle. We see a similar kind of thing in this beautiful ceiling. This is from a mosque in Iran, and again you have just a delightful repetition of the shapes going around in the circle. Symmetrical and repeating patterns and designs are seen a lot in Islamic art, in part because of the prohibition of showing living things and representing them. Here is a wall in the famous Alhambra Palace in Spain, and this is a Moorish palace, and we see here lots of different kinds of tilings, repeating patterns that create a lovely decorative effect. We don't just see it in decoration in art, but also in the architecture itself. So the Taj Mahal, which is often said to be the most beautiful building in the world, you can see here, this is an example of where we have what's called bilateral symmetry, so a vertical mirror line down the side, down the middle of that building, and it looks the same on the left and the right. But also, by the clever use of the shallow lake here in front, there is the illusion given of another line of symmetry, a horizontal mirror line, because of the reflection of the building in that water. If you want genuine more symmetry in architectural design, this villa in Italy, the Villa Rotonda, which was designed by Palladio, we're looking at it from the side, and you can see that the two facades here that we can see do look the same as each other, and they also have internally a bilateral symmetry. But if we look at the original design for that building, we're looking now top down, you can see it's a square design with a circular rotunda, and we can also impose another circle onto that for an extra added bit of symmetry. We can see the corners of the building, the four corners of the building, pass through that circle, which also passes through the four colonnades. So all of the front facades look like each other. There is a lot of symmetry happening in that building. Why do we like symmetry as humans? Clearly we do. We enjoy it. It pleases us. We like to look at it. This is not a beautiful picture. We'll get rid of this as soon as we can. But this illustrates what we call the perceptual bias view of symmetry, why we like it. It's literally easy on the eye. And if you look at this picture for a while, a photograph of a tiling disaster, once you notice the problem with it, you cannot stop seeing it. There is one tile out of place in this not very nice office floor, right? If you did that, you would be kicking yourself for some time. It's a snag in our brains. We have to work harder to process that image because it's like repeat, 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 lovely, 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 and then lovely, lovely, lovely again. So it's harder for our brains to process and understand, whereas a beautiful symmetrical design, it's the same on the left and the right, it's the same all the way around. That's easier for us to look at. So we like it for that reason, is the theory. There's another theory, which is called the evolutionary bias theory, which says, our primitive, silly animal brains, which are still part of our brains, when, wanting to pass on our genes, we want to, mate with a animal that is healthy, and symmetry in an animal's body is perhaps a proxy or some indication of good physical health, and so that may be a reason why we like symmetrical things. Nobody really knows for sure, but those are two theories. So given that we like symmetry, we find it appealing, we find it beautiful, people have associated symmetrical, beautiful things with virtue, with goodness, and even with the divine. And this goes back a long time. So if we go back to Plato, for example, 360 BC or thereabouts, writing in this dialogue, the Timaeus, about the creation of the universe, he is explaining, modern science, a method with which your scientific training will have made you familiar. We are going to work out, what the universe is made of and why. So fire, air, earth, and water are the four elements, right? We all know this. They are bodies, so they're solids, and we must determine then what are the four most beautiful figures, because of course the creator of the universe everything they do is perfect. They will use beautiful things to make up the universe. So we all know there are 4 elements, so therefore we must find the 4 most beautiful solids. Here are then the 4 most beautiful solids according to Plato. There is a gap in this picture, and we will fill that gap in a moment. So up there you've got on the top left, you've got the tetrahedron, then the octahedron, then the cube, and then on the bottom you've got the icosahedron. So how do we match those up? Plato has to tell us which one matches to which of the 4 elements. Well, obviously, fire, when you touch fire, it hurts. It sort of prickles and it's nasty to touch. So it obviously must be the one that has the most pointiest shape, which is the tetrahedron, right? And by contrast, water slips through our fingers and it feels lovely. And so that must be the shape which has the kind of softest angles in it. So Plato tells us that's the icosahedron. Icosa because it's made of 20 equilateral triangles. Icosa is the Greek for 20. So that's water. And then earth, that's the only one of these that you can actually build a solid structure out of. So that must be associated to the shape that you can do that with, where you can pile up things of that shape without any gaps or without it falling down. And the only one of those shapes you can do that with is the cube. So that's earth. And what's left? The octahedron in the top, in the middle there. And so that must be air. Right, so science. But Plato there's a gap, because Plato has not 4 solids, actually, that he needs to pigeonhole into his view of the universe. He has 5 solids. And he's got to find a use for this other solid. So this is an example of, an all too human thing where we've got something a preconceived idea we want to make fit the data. So he's got 4 elements, but he's got 5 solids. It's quite clear, there's a 5th figure, he says. It's made out of 12 pentagons, there it is. It's called a dodecahedron. And this, God used as the model for the 12-fold division of the zodiac. Okay, so what this tells us is Plato has 5 solids that he thinks are the most beautiful. And he wants to put those into his understanding of the universe somehow. So that's the way he does it. But for us, now, our question would be, why? Why are there these 5? Where does he get these 5 solids from? And in order to understand that, we need to think about, I would say these are the most symmetrical solids, but what do I mean by that, and how can we tell? Where do we get these 5 from? So we need to think about how we measure symmetry. What does it mean to say something is more symmetrical than something else? So I'm now going to sort of take a more modern, this is our modern mathematical understanding of symmetry. It's not quite how Plato would have expressed things. But in a kind of informal way, we can say a symmetry is something you can do to a shape that leaves it looking the same. So if I were to take this isosceles triangle here, and you were all to close your eyes, and then I were to do something to it, and then you open your eyes and you don't know I've done anything, not the greatest example for a lecture, right? we will talk about what we're going to do. Then I would have done asymmetry. You can be a bit more mathematical, if you like. You can say something like a distance-preserving transformation that maps the object to itself. In other words, I don't want to stretch anything. We're not doing topology, we're doing geometry. We're not stretching things. We're just doing something to the shape like we might, reflect it in a vertical mirror line, like we're going to do with this isosceles triangle, or rotate it or move it around like that. But we're not stretching anything. So the distances between points are going to be the same before as after. So this isosceles triangle, it's not equilateral, it's isosceles, so it has 2 sides that are the same, but then it's got one shorter side at the bottom. So what are the symmetries of that? Well, there is a nice vertical mirror line we can draw. You can flip it left to right, and it will look the same after you've done that. There's one other symmetry, which actually any shape, however weird and wonderful, has that symmetry, and that is don't do anything. So it looks as if you haven't done anything because you haven't done anything. It leaves every point identically where it is, and so we call it the identity map. So this is the do-nothing the do-nothing symmetry. Every shape will have that, however weird it is. So the isosceles triangle, it has 2 symmetries. Now, how can we be sure there aren't any others? Maybe there's something I haven't spotted. Well, we're limited with this shape. The reason is that if your shape is going to look exactly the same afterwards, after whatever you've done, then you've got to map the vertices, the points, to vertices. So those 3 points there have to be somehow rearranged in some way. You've got to map edges to edges, and you better map an edge of a given length either to itself or to another edge of a given length. So the 2 long sides could potentially be swapped over, and that's what happens with the reflection, or they could be left where they are. But this short side at the bottom, there's nothing for it, it's just got to stay where it is. So with the reflection, it turns it over on itself, but it still gets sent to itself. So because of that one kind of odd one outside, we're limited because that side always has to just end up back where it started. So if only we had a triangle where all the sides were the same length, we would hope that there would be more symmetry happening there. And another thing we'd better have is that, if a pair of edges are meeting at a particular angle, then after you do the symmetry to them, you shouldn't be able to tell that anything's happened. So they'd better still be meeting at that particular angle, maybe somewhere else in the shape. So the things that are going to be the most symmetrical are likely to be shapes where all the edges have the same length and all the angles are the same, all the angles are equal. For example, an equilateral triangle. So here we get a lot more symmetry suddenly because there's more freedom of movement, so to speak. There are now 3 reflection symmetries, so I'll draw you the mirror lines. So there's that vertical line, but we can also have one coming out of any vertex and crossing the middle of the opposite side. So there are 3 reflections. We can also now start doing rotations. So we can take this triangle and rotate it 1/3 of the way around, or 2/3 of the way around. And you always, for free, get the do nothing, the identity map. Leave everything where it is. So that gives us now 6 symmetries. So we can categorically say, this is counting, we can say the equilateral triangle is more symmetrical than that isosceles not equilateral triangle. And we can take this further. So we can talk about polygons in general. So polygons, 2-dimensional shapes made with straight lines. So the most symmetrical kind of quadrilateral, right, 4-sided shape, it ought to be one where all the sides have the same length. So that would make it a rhombus or a diamond. But we would also like all the angles to be the same, and that makes it be a square. So the regular polygons, so-called, they're the ones where all the sides are the same length and all the angles are equal. Here are the first few. The first 2 have special names: equilateral triangle, square, and then you just say regular pentagon, regular hexagon, regular n-gon, if you like. And these are the most symmetrical of their kind. In other words, if you have a 7-sided shape, the most symmetrical you can hope for is a regular heptagon. It will have 14 symmetries, it turns out. So you just double the number, and that's how many symmetries there are. Now, you can take this to the limiting extreme, and what you would end up there with is a circle, and that in fact has infinitely many symmetries to it, because any diameter you can reflect in is a line of mirror line, and you can rotate about the centre through any angle, and it will still look the same. So these are kind of the regular shapes, the regular polygons in 2 dimensions. Well, now we've done that, so warm up, let's go up to 3 dimensions. What would we think would be the most symmetrical? And it's not polygons now, it's polyhedra, the 3-dimensional shapes you can make with straight lines. Well, by the same kind of reasoning that we've used, what you want is, if you want the most symmetry, you want all the edges to be the same length. So the faces of these things are going to be our regular polygons, so equilateral triangles, squares, and things. And you will want the same number of these faces to meet at any point, because then that gives you the most freedom of movement in terms of rotating things and moving it around and still leaving it looking the same. So that's the definition of what we call a regular polyhedron. All the edges are the same length, the same number of faces are meeting at every point, and these faces are regular polygons. So what actually could we get? I mean, let's just sort of think about it for a little bit. Suppose we're trying to make one of these things, these regular polyhedra, from equilateral triangles. So all the faces are going to be equilateral triangles. How many of these could meet at a point in our 3-dimensional shape? Well, if we tried to do it with 2 meeting at a point, that's no good. It's just going to flop onto itself. That's never going to work. If we have 3 meeting at a point, we could try and, can we make a shape like that? Or 4 meeting at a point, or 5. All of those work. Here they are. 3 at a point is the tetrahedron. 4, octahedron, so it has 8 faces. 5 is the icosahedron. That was the one that Plato said was representing water. These pictures, by the way, were drawn by Leonardo da Vinci for a 1509 book by Luca Pacioli on proportion and art and lovely things like that. If you try to get 6 of these equilateral triangles round a point, well, the angle in an equilateral triangle is 60 degrees. So 6 of those makes 360. So that's actually just going to give you a flat surface. It's never going to close in on itself. You can't make a three-dimensional solid. So that's no good. So 6 won't work. Anything higher than 6, it gets even worse. The triangles are overlapping, so that's no good. So that's all we can do with equilateral triangles. Squares, what about them? Well, again, 2 squares, just going to flop. 3 squares, yes, that gives you a cube, which actually you can see, but it's very small writing, but it says that's called a hexahedron by some people because it has 6 faces, right? If you try 4 squares around a point, well, the angle in a square is 90 degrees, so 4 of those makes 360. Again, you're going to get a flat surface. 5 and up. Can't be done, they overlap with each other. Pentagons, 2 isn't enough. 3 is all right, dodecahedron. 4 is too many, they overlap. With hexagons, 2 is too few. 3 hexagons does make 360 degrees exactly because the internal angle is 120. So that again would give you a flat surface. 4 and above, overlapping, doesn't work. Anything more than hexagons, 2 is too few, and 3 round a point would already overlap, and you'd have too many. So that's why. That's why we get 5, exactly 5, no more, no less, of these regular, highly symmetric three-dimensional shapes, the regular polyhedra, and these are called the Platonic solids. And, I really like, so I've been a bit sort of slightly laughing at Plato and the 4 elements and the extra thing, the quintessence, right, the 5th element, that's what that word quintessence means, because he's got these 5 things already and he puts it into the science of the time. The science has changed over the years, of course, but the mathematics, one of the things I like about maths, it's true. It was true then, it's true now. And it will always be true. There will always be these 5 regular polyhedra that we've just proved. That's what there are. So, yay maths. So here we are. We've got these lovely symmetrical shapes. Those 3 times where we said, oh, this number of those shapes just exactly equals a 360-degree angle, so these are sort of the limiting conditions, that happened 3 times for triangles, squares, and regular hexagons. They're not wasted because they give you precisely the 3 ways to tile the plane with regular polygons. And there they are there. So those things that we just noticed on our way through the argument, that's the use of them. That's where they crop up. Well, Plato was talking about these solids in 360 BC. They also appear in Euclid's books. Were they known before then? Periodically, you will hear this claim made that actually these solids were known a long time before, hundreds of years before Plato, to Neolithic peoples. And it's because of these kind of stone balls that have been found in archaeological digs in Scotland. Hundreds of them have been found. And this is a picture where someone has helpfully kind of added in kind of little white strips of paper to emphasise the shapes that they see. So my question, are these really Neolithic Platonic solids, or are they a load of old balls? Let's discuss. Here is the evidence for. Some of them do look a bit like Platonic solids. The evidence against. If you take off the white bits of paper, you get things a bit more like that, which you may not necessarily, if you've never seen a Platonic solid, you wouldn't necessarily think, oh, those look like highly regular designs. There have been several hundred of these shapes found, of these stone balls found. All of them have some combination of kind of lumps in them and indentations carved out of them. Now, if you want, say, a cube, you want to say one of these represents a cube, then a cube has 6 faces, and it has 8 vertices. So kind of the lumps that you have, they potentially could represent either faces or vertices, depending on their size. So if you see something with either 6 or 8 of the lumps, then that maybe could represent a cube or perhaps an octahedron. If you have 4, then that could perhaps represent a tetrahedron, which has 4 vertices and 4 faces. And the dodecahedron and icosahedron, they have 12 and 20 faces or vertices. It's, they're dual of each other. So if you're looking at these things, you have a collection of them. If you see that they all have almost all have 4 or 6 or 8 or 12 or 20 lumps on them, then that would be a good indication. The problem is that they don't. So loads of them have 6, loads, about half of them. But only, I think, 8 of them have 12 lumps and only 2 of them have 20. So it's really not very convincing. And all of the others just have, I won't say random, but they have different numbers of these indentations and lumps on them, ranging up to, over 100, maybe 120, 130. So it's not really very compelling, I would say. I do not think that Neolithic people knew about the Platonic solids, or at least they didn't have a classification of these solids. The sad thing really is that there is so much that's fascinating and interesting about the archaeology of Neolithic times that I don't think we need to map onto it our modern views and understandings to find it really interesting. So I would say no to Neolithic Platonic solids, but yes to archaeology being really, really fascinating, and let's find out what they really were doing. We don't really know what the purpose of these objects were. If you want Platonic solids in architecture, in archaeology, you can have them. You can have them, but you have to wait until Roman times. For these bad boys, these are dodecahedra, or this is dodecahedron, and there are loads of these been found in the remains of Roman settlements. We don't know what they're for. Answers on a postcard. They tend to have these circular holes in the pentagonal faces, tend to all be different sizes, so it's been suggested that they were perhaps used for gauging pipe widths, or perhaps for surveying in some way. Other people have said maybe it's something to do with, knitting or weaving, something like that. Nobody really knows. Are they gaming pieces? We're not sure, but they are dodecahedra. Very lovely things. So we're not absolutely certain when the Platonic solids were discovered, but it's nearer to Plato's time than to Neolithic times. The curious thing, I want to give you, words are interesting. This word symmetry that we're talking about, curiously enough, you don't get it. So even in the books of Euclid, where the Platonic solids are discussed and obtained, in book 13 of Euclid, I think, the word symmetry is not used. They are just kind of equilateral figures with equal numbers of size, things like that. But there isn't the use of the word symmetry. I mean, of course, not the English word. Even though there is a Greek word, and it has a Greek root, symmetria, symmetros. It comes from 2 Greek words. The first bit means together, and metros means measure, so it's sort of measured together. And you do get that word, but it doesn't mean anything to do with what we would think of as symmetry. It's used in a rather technical, geometrical sense. It's used to mean where you have 2 numbers or magnitudes, lengths, that have a common measure. In other words, they are both whole number multiples of a common thing, the same thing. So when these texts start to get translated into Latin, there isn't a word in Latin for this either. So you have, Pliny saying, we don't have a Latin word for symmetria in this context. So he translates it not as symmetria, but as commensuratio, from where we now get the term in geometry of things being commensurable. But that's where that usage went. And that's really the only time you see that word. And it's kind of a false friend, because it doesn't mean symmetry like we think of it as symmetry. There is another use in Greek. So Aristotle uses this word, symmetria. And he is talking about the species of beauty. Of course, there are 3, because it's Aristotle, and he has 3 of everything. And the middle one is proportion. Well, what we now call proportion, which is in the Greek symmetria. Of course, they are revealed by mathematics, like all things. But this word now, this usage of the word, proportion, harmony, things going together nicely, that goes across to Latin. And that's in Latin, if you see the word symmetria, as used, for example, by Vitruvius in books about architecture, it has that meaning of proportion, not what we would call reflections, rotations. That's not what is being meant there. So this symmetria becomes 2 things in Latin: commensuratio, which we won't talk about at the moment, and proportion, which we also won't talk about today very much. We're talking about our modern word symmetry. We will talk about proportion in my next lecture in February. Just a little advert there. But symmetry or symmetria then is the harmony arising out of the details of the work, the correspondence of details to the whole. You know, if something is in a 2-to-1 ratio over here, it ought to be in a 2-to-1 ratio over here, even if it's enlarged. So something happens, like we skip forward, 1,500 years. By the time people are translating Vitruvius into their own languages, particularly in France, this word has acquired slightly different meaning. So Claude Perrault, who was an architect, he's most famous for the thing I've got the picture of there, the colonnade of the Louvre. He says symmetry in French, that word now in French doesn't quite mean the same thing anymore. Vitruvius, it's all about proportion. But now, in 1673, it now has come to mean in French things being the same on the left and the right. So this is starting to be our modern understanding of what we mean by symmetry. So in French, he says, the windows in a building, the same distance from the centre on the left and the right. If the distance is unequal on one side, it's also unequal on the other in the same way. And of course, this facade here, this colonnade, does have that bilateral symmetry. It's a very beautiful thing. So we get this slightly new understanding of symmetry, but what really starts to make it amenable to study by mathematicians is it's almost like a psychological change in our understanding. Because in this building here, we can say it has symmetry. That's a very static thing. It's just there being beautiful. We start to get, it's the first instance of this, a mathematician, Legendre. This is not me being mean and putting a horrible caricature. It's not. It's a nice caricature. But this is the only picture of this guy. Until 2007 or thereabouts, books which talked about Legendre, the mathematician, had a picture of someone called Legendre who was a totally different person, nothing to do with him. And it was an all kind of nice politician picture, all statesman-like. This is the only picture I have of him. So there we are. And you can see he's a mathematician because he's got A plus B equals X written next to him. So, and a nice proof of Pythagoras' theorem above his left ear. But there he is. Now, he wrote a book about geometry, and I just want to highlight this little phrase from it because this is the start of our whole modern understanding, I would say, mathematically, of symmetry. Because here, forget most of the words, but you've got this little phrase, angles are equal by symmetry. Symmetry is something that is happening. It's not just there, statically, it's happening. These things are equal by symmetry. You're doing something to them. You're starting to verb this word. It's becoming an active relation. It's rather like what happened, actually, a century or so earlier, when Descartes, in geometry, started to think about curves not just as being there, but as representing a dynamic relationship between variables, between your x's and y's, or between things as they changed over time. That laid the foundations for calculus. This understanding of symmetry as being a more active thing, what did that lay the foundations for? Well, a wonderful area of mathematics called group theory, which I'm going to tell you a teensy-weensy bit about because I love it. When you start thinking of symmetries as being things that are actively happening to shapes, then you start to have interesting thoughts. For example, you might notice something. The composition of any two symmetries is another symmetry. So what I mean by that, so here's a square. We know we can do like a rotation, a quarter turn, 90 degrees. If you do one of those and then you do another one, well, after each symmetry, the shape looks the same. So if you do one and then you do another one, the net effect of that should still be a symmetry because it will still look the same after you've done both of those. So this is kind of what we call a closed set in the sense that when you combine any two elements of it, you still get something that's in the set. So this is true for symmetries. Another example is in a square. If you do a reflection, it's got a reflection in the vertical line. That's certainly a symmetry. You can also reflect it in the horizontal line. That's a symmetry. So the combination of those two things ought to still be a symmetry. Now it's less clear, perhaps, what symmetry it might be. And of course, I can't show you because when you do a symmetry to a thing, it looks exactly the same afterwards. So I thought about how to show you what happens with these things and decided to shamelessly appeal to things we all like looking at. So here's an adorable little puppy who will be helping us with our experiment. So adorable puppy will be rotated through 90 degrees. No puppies were harmed in the making of this slide. Rotated through 90 degrees anti-clockwise. There he goes. And then we'll do that again. And there he goes again. So the poppy, of course, does not have rotation through 90 degrees as one of his symmetries, but the square does. And you can see the net effect of this, as we might have expected. It is a rotation through 180 degrees. We've done a half turn. Okay, let's see what happens when we take the same very willing puppy and try doing these reflections. So if we reflect in the vertical line, okay, that happens. And then if we reflect in the horizontal line, that happens. And oh, look, we've ended up in the same place. So, a square would look the same throughout all of this, so we wouldn't be able to see it. But you can see, when you do those two reflections, one after the other, the upshot is a rotation. And it's the rotation through 180 degrees that we already know is a symmetry. So this is just sort of showing you in this case, yes, the composition of these two symmetries is still a symmetry of a square. But this is always true for the symmetries of any shape. You can combine them and the outcome is still another symmetry. So they have this closure property. There are a couple of other properties we've seen. We've already seen that every shape has this identity symmetry, the do nothing, leave everything where it is. That's always in there. It's an element of the set that hasn't, leaves everything fixed. And there's another point, which is that you can always undo a symmetry. So if I've rotated 90 degrees anti-clockwise, I can undo that by rotating 90 degrees clockwise. Let's just put this poor puppy out of his upside-down state by doing the inverse right here. So we've undone our reflections, we've undone our rotations. You can always do this. So these three properties of symmetries, the set of symmetries of any shape, they are not the only time in mathematics that you see collections of objects or sets that have these kind of properties going on. The set of symmetries of a shape is one example of the mathematical structure called a group. So a group is a set, but with some stuff, with some structure on it. Now, groups, I haven't told you what they are yet, but they just sort of exploded everywhere in mathematics in the 19th century. It was pretty amazing. The first person to use the word group was the mathematician Évariste Galois in about 1830-ish. And he was not doing anything to do with geometry, or at least not knowingly. He was studying equations, polynomial equations, like quadratic equations, cubic equations, and trying to work out which ones could be solved and which ones couldn't, in a very broad brushstrokes way. And he noticed that if you've got solutions of these equations, sometimes you can permute them, you can swap them with each other and jumble them around and still end up with solutions. So he noticed this, and he noticed these permutations, whatever they are, could be composed and still result in more permutations or shufflings. And so he looked at these collections of permutations and he said, right, I'll call this a group, and then he proved some stuff about groups. Later on, they showed up in study of symmetry, in geometry, but they also appear in numbers, in functions, all over the place. And here are the stone tablets upon which the axioms of a group are written. And this is often how, if you go to university and study groups, you will be given, like day one, here are the rules. And it's not necessarily clear why these are the rules that are chosen, but I'm telling you now, it's because these things are everywhere. So they're in symmetry, they're in solving equations, they're in functions. We've seen 3 of these rules already with symmetries. I'm just going to give you one example, without really too much detail about it, showing actually numbers can form these structures as well. So if you take whole numbers, integers, so 0, 1, 2, 3, and then -1, -2, and so on, we can combine whole numbers by adding them together. So with symmetries, we do one, then we do the next one. With numbers, what you do is you add them. And if you do this, you find that you have these properties. So the closure that we talked about, if you add together two whole numbers, the answer is still a whole number, an integer. 3 plus 7 is 10, 10 is a whole number. So that's always true. There's a number that when you add it, nothing happens, and that's 0. So add 0 to any number, that nothing happens. That's like our identity symmetry. Inverses. How do I undo adding 7? Well, I take away 7 again. So we can always do that. So that's true for these numbers. And then the final one, this associative law, which is it's a bit of a technical condition, but I've just written it down here just to show you. And that sort of says you can bracket up your calculations without having an effect on the ultimate outcome. So, 3 plus 7 plus 2 is the same as 3 plus 7 plus 2, right? And that will be true for any numbers. So that something like that is true for all symmetries, but I didn't want to go into it. So these rules and these structures crop up everywhere. Numbers is another example. The point of doing this, or of realizing that this structure appears, is that if you just have those starting points, just those 4 rules, and you can prove things, you can make deductions about what happens just with those assumptions, then anything you can deduce, get a theorem that's true for groups, that will be true for symmetries, for numbers, for functions, for all of the places where it crops up, everywhere in geometry. So it's a really, really powerful thing to understand and to study. But since we're talking about symmetry, let's have an application or something we can use this for in the context of symmetry. So I want to talk about friezes. So these are decorative patterns that you find, in art, in the borders of rooms, carpets. You find them in illuminated manuscripts all over the place on buildings. So what mathematically a frieze pattern would be a design that goes along a strip that could be continued indefinitely if you wanted it to, and there is some symmetry there, but in particular, one symmetry you always have in a frieze pattern, it's got a repeating design, so you will always have a translational symmetry. You could shift the design along the strip and it repeats. So that's always in there, but then there might be some other symmetries. And what we're going to do, at least hint at doing, is to see that actually this understanding that what we have here is this thing called a group can help us to get a feel for what the different possibilities are for a frieze. So, of course, there are as many patterns as you like, only limited by your creativity in terms, I'm not saying there are only finitely many patterns you can put on a frieze. There are lots and lots of patterns you could design, but the potential symmetries you could have are going to be something we can explore with this idea of a group. And in particular, the fact that if you have 2 symmetries, then the composition of those, doing one then the next one, must also be a symmetry. So the design you're going to repeat determines what those possibilities are. And here is a case where it's not enough to just count the symmetries. Say, this one will be more symmetrical than that one because this one has 9 symmetries and this one has 12. Every frieze has infinitely many symmetries because you can just do this translation, 1 step, 2 steps, 3 steps, and so on. So when you have infinitely many symmetries of all the friezes, then you need a bit more sophistication to be able to understand what's going on. So there's another symmetry down at the bottom. I've allowed this to be a frieze. It's a design on a Mesopotamian pot. Of course, it goes all the way around, so you could say it's indefinitely extended. What possible symmetries of these things can we have? Well, here are some. So if we look at the design on the top, there you could reflect it in the central horizontal line, like that, and it was still the same. You could reflect it in some of the vertical lines, like through key points in the design, so there are reflections in vertical lines. You potentially rotate through 180 degrees about various points on the central line. You can't have rotation through anything other than 180 degrees, though, because the first thing you have to do is leave the strip in the same position. So if you rotate through 74 degrees, you're going to get a wonky strip that won't look the same. So those are we can only really hope for those. Now, the design on the top has all of those things, but the design on the bottom, it's got these zigzag patterns. If you try and do a reflection in the vertical line or rotation, then the zags will turn into zigs and it won't look the same. But you can do a reflection in the central horizontal line if you want. There's one other symmetry that can occur, and this is what a beautiful frieze design. So this footsteps, we want to capture somehow that, we've got left feet and right feet, and they are the mirror image of each other, but we can't just do a straight reflection because they're a half step separated. So the answer is that we do what we call a glide reflection, which is where you go, literally in this case, a half step and then reflect. So go half a step and then reflect the design, and that turns the left feet into the right feet and so on. So that is another kind of symmetry you might end up with. So we've got a few candidate symmetries for friezes. And now we can bring our group theory understanding into play. We know that if we have 2 symmetries, then their composition will also be a symmetry. So we can't get all possibilities that we've just mentioned occurring completely independently. For example, Our puppy friend earlier showed us that if you have a reflection in a vertical line and a reflection in a horizontal line, then the composition of those two things is rotation through 180 degrees. So if we've got those two reflections as symmetries of our frieze, we must have the rotation as well. So those kinds of considerations and a bit of thinking and exploring allow us to actually classify all the possible frieze groups that you can have. There are 7, which I think is quite nice. There are 7 possible different kinds of symmetries of friezes, collections of symmetries, these groups. I won't enumerate them now, but there's a picture of this in the transcript you can have a look at, and I encourage you to become frieze detectives on your walking around the town you live in. Just have a look at, we might look, this one up there is quite popular, the egg and dart design. You see that on a lot of buildings. That only has vertical reflections, right? But you can have a look at all of these. There's the crib sheet for what the possibilities are. So there are 7 frieze patterns, and to understand what those are, you need to understand a bit about the mechanics of the groups that are underneath them. So friezes, that's a little example. We've talked about how this idea of a group was everywhere in the 19th century mathematics. The idea of symmetry, similarly, seemed to be everywhere in 19th century science. And part of it, I think, was that microscopes got a lot better. We could look at the structure of things a bit better. So we get the law of symmetry for crystals in 1815. The way in which nature produces crystals is always that of the greatest symmetry. Opposite and corresponding parts are equal in number, arrangement, and shape. Got there, that's a fluorite crystal, isn't it? Lovely octahedral structure. And what's going on there, as we now know, crystals are arrays of atoms that are put together in a structure that repeats because, we have this symmetry because what works in one direction works in all the directions, right? So if you're understanding, of course, you need something a bit more complicated than friezes, which are just strips. Crystals are 3-dimensional, but they are made of 2-dimensional slices. So we need to understand, to begin with, it's going to help us to understand what kind of symmetries you can have for the slices to cover the whole plane with repeating designs. This is not the beautifulest picture, but it's taken from a book about crystallography. And it shows you here that there are, in fact, 17 of these kinds of symmetries, symmetry groups, where you are filling the plane in a repeating way. So we call these the 17 wallpaper patterns. Now, this has a very profound impact on art because the artist M.C. Escher produced lots of beautiful designs based on tilings. He was inspired by a visit to the Alhambra Palace that we saw a picture of earlier, and he was trying to understand what the possibilities were. His big brother was a professor of geology, and he said, you need to look at what the crystallographers have done. They've classified all of these possible tilings. And this is a picture from a textbook that just is doing that. Crystal on the left there, iron parietes, beautiful. It almost looks impossible that could be a naturally occurring thing there, so perfect. So we've got these 17 wallpaper groups that allow us to understand the possibilities in 2 dimensions. Crystals are 3-dimensional. If you want to go up to 3 dimensions, again, the maths gets a little bit more complicated, same underlying ideas. There are 230 of those. I'm not going to show you a picture of all of those. But, in art and design, we see experiments and work that uses tessellations and tilings, and not just with Escher, but right up to the present day. This is a lovely fish design by the digital artist Chris Watson, whose website is rather pleasing. Lots of these lovely images that are quite appealing, hexagons and triangles happening there. But you see these things on your travels out and about as well. So if you are in London and you've come here today in person, you may have sat on an Enid Marx on your way here, because Enid Marx, she's on the top left with a lovely little cat on her shoulder. She designed many of the fabrics on London Transport. And if you are living in London, you get different fabrics for each of the different bus lines and tube lines, and you have repeating designs made in fabric. So, of course, those will need, they will all have different symmetries attached to them. On the top right there, you've got Orla Keeley. Who among us does not have an Orla Keeley tea towel or something like that in our house? Again, repeating designs that look very pleasing. Bottom left, Zara Hussain, who's a Walthamstow-based artist. And she's classically trained in traditional Islamic art. She produces these wonderful designs, and the designs are all, she does these ruler and compass constructions of beautiful geometric, symmetrical tilings, but then she also uses modern technology to overlay some of those designs using light to make beautiful installations like the one that's shown there, which appeared at the Barbican a few years ago. And I thought I'd have a token man. So here's William Morris, much loved wallpaper designer, among other things. From forever, people have been wanting to cover walls with beautiful things, and we can see mathematically there are 17 ways to do it, upon which you then overlay your artistic designs. Nature also uses symmetry. Now, complicated animals like humans, we are restricted a little bit in what we can do because we've got gravity acting on us, so our tops and our bottoms, our head and our feet are we lose some symmetry there. With more constraint becomes less symmetry, right? We have to move around, we have to see things, so we have a front and a back. So really the only kind of symmetry available to very complex organisms is the bilateral symmetry that we mostly have. But something like a starfish has got a little bit less going on, so that starfish can have a beautiful five-fold symmetry in its design. If we go to even simpler organisms, here is a picture drawn by Ernest Haeckel. He went on a sea voyage and he looked at tiny sea creatures called radialara through a microscope, and he drew what he saw. And these are very little creatures. They're just bobbing up and down in the ocean. They're so small that they're not really affected by gravity. They haven't got eyes or anything. They're very simple organisms. And that means they can be very symmetrical. And it's just, I'm still, every time I look at this, it's amazing. Because look, there are Platonic solids. There is an icosahedron right in the middle there. This is an animal, and it's got this amazing symmetry. So these things really are in nature. These fantastic pictures drawn because microscopes got good enough to see them. So we see these ideas in nature, as well as in crystallography, and of course in mathematics and art and design and architecture. And in mathematics, you think, what's this got to do? Of course, Dido's very pretty, but that's not what I'm showing you this picture for. I want to just illustrate for you one way in mathematics and science that the idea of symmetry is very useful is because for the same reason as those little tiny sea creatures could be symmetrical because they had fewer constraints on them, kind of the converse of that is that you can use the idea of symmetry to improve solutions that you have for a problem. Because if something works in one direction, you can use symmetry. You can say, by symmetry, it ought to work in this other direction, unless there's some constraint that we have to consider. So Dido, she's in this story because of the legend that she had to, for convoluted reasons, had to flee her home country, and she landed up on the north coast of Africa. She had some money, but she didn't have anywhere to live. So she discussed with the people who were living there, could she buy some land to settle on? And what they agreed, and I know they may have thought they got a good deal, what they agreed was, she said, I'll give you all this money, and all you need to give me in return is the amount of land that can be encompassed by the hide of a single ox. So they were like, okay, all right. So she said, okay, good. So once they'd shook hands, she took the hide of this ox and she cut it into little tiny strips and she tied them together, and so she ended up with a big rope. And then she could encompass a lot of land in that. But mathematically, you can say, what is the most amount of land you can encompass with a given length of rope or ox hide strips tied together? And we can use an argument that involves symmetry. So let's suppose you just chuck your bit of rope down and you get some shape like this. Then you can say, right, anywhere I cut this so that I've got half of the length on one side and half of the length on the other, I can have a look and I can see which half has got the most land in it for that length of string or rope. And when I do that, then I can just reflect that solution, and that will increase the other half to be the same as, the best half so far. So you can do that, and you go, okay, now I've got this shape. Then you can do it anywhere else. You can repeat this same thing as often as you like. So we draw a line through somewhere else, and we say, okay, I've got more land encompassed in the top half there, so I will just reflect, by symmetry, I can increase the optimize and optimize and optimize, and I can keep going, and I keep going, and I end up with the perfectly symmetrical thing, a circle, which is indeed the solution to the problem, what shape gives you the most amount of land inside a given fixed perimeter length. Now, it takes a bit of work. I've brushed under the carpet some of the detailed mathematics that involved in proving that this is like a unique optimal solution, but it's a very appealing intuitive argument that does give you the circle as one optimal solution. So this is one way in which we can use these kind of arguments in science and in mathematics. Use the argument of symmetry, it gives you the best solution. I want to go back for the last couple of minutes to talk about the ongoing importance to our psyches of the symbolism of symmetry. So we saw how Plato loved these 5 solids and wanted them to fit into his understanding of the universe. This desire, this kind of perception, symmetry is great, it's beautiful, it's virtuous, it's divine, it has lasted and it is still with us. This is quite an old picture, but even almost 2,000 years after Plato, Kepler was absolutely enamoured with the Platonic solids. And actually, the picture I showed you before with the diagrams with the fire inside the tetrahedron, that came from a book that Kepler wrote. Kepler's famous now because he understood about the elliptical orbits of planets. He was studying planetary science. He loved the Platonic solids. He had a problem, which wasn't that he thought there were 4 elements. I'm not sure what he thought about the elements. But his question was, we've got these planets, 6 were known at the time, and the average distances from the sun, we know what they are. But why? Why are they those distances from the sun? God must have had a reason for doing that. What was the reason for doing that? And he was so familiar with the Platonic solids that he actually recognised that the distances, kind of the relationships between these average distances were very similar to, and up to experimental error, the same as the distances between the spheres you can draw, kind of inscribed and circumscribed spheres of a nest of Platonic solids, as long as you nest them in the right order. So there are lots of different ways to put them inside each other. And this picture, it's got a tetrahedron and then an icosahedron, and then they're all in there, getting smaller and smaller, and you draw these spheres just touching the insides and the outsides, and they give you the average orbital distances of the planets from the sun. So it's a lovely picture. There is a slight problem in that we now know there are more than 6 planets. So unfortunately, this can't be true, or it can't be, you don't necessarily need a reason, but the fact there are more than 6 planets means this is not going to be extendable to the other planets we know about. But this shows again, this absolute, the love of the symmetry of these things makes people want to use them in their efforts in various spheres, literally. Coming more up to date, so symmetry has this symbolism to do with beauty, but also it has a symbolism to do with equity and fairness. So here is a picture that I want to show you. This is from 1902 or thereabouts. It's from a book called Garden Cities of Tomorrow. And the influential town planner Ebenezer Howard, who was kind of really an instigator of the Garden Cities movement, drew this picture, or this design, of a group of slumless, smokeless cities. So these are the cities of the future. They're healthy places to live. Everyone has equal access to everything. Everything that you need is there for you. You've got this central city and then a symmetrical design around the outside with a hexagon of smaller towns and cities. Because it's a hexagon, it's made up of equilateral triangles. So adjacent cities, they're the same distance from each other and from the central city. So this real sort of sense of fairness that everyone has equal access to the facilities, the opportunities. There are farms, there are facilities you might need. Some of the language is a little bit antiquated. I've just blown up the middle bit, then you can see there's the home for inebriates next to the reservoir and waterfall. Very nice. And there's a home for waifs, and there's an epileptic farm, which has a slightly odd ring to it nowadays. But, there are other things. This is supposed to be a peaceful, pleasant, pollution-free place. And we can see that in the symbolism of the fairness given to you by symmetry. Now, there's another thing you can do with symmetry. When you understand the rules, then you can decide whether or not to break them. So I'm going to finish with this picture it's attributed to Giotto. It's called the Baroncelli polyptych. This is a very symmetrical thing. It's got 5 panels, and the 2 on the left and the 2 on the right feature, I think it's 51 saints on the left and 51 saints on the right, and 10 angels on the left and 10 angels on the right, and they're all looking towards the central panel, which features the Virgin Mary being crowned Queen of Heaven. So all the symmetry is drawing your eye in. But if we focus in on this panel here, and we just enlarge it a little bit, can you see what's happening there? One person, all of the 51 saints and 10 angels on the right are looking towards the centre. All of the 51 saints on the left and 10 angels on the left are looking towards the centre, except for this guy who's looking somewhere else. Now, why? That's a conscious decision. It's clearly a conscious decision of Giotto to do that. Why has he done that? There will be a reason. He has chosen to break the symmetry. In this case, someone will tell me the exact... I don't think anyone really knows, but, could this be a self-portrait sneaked into the picture? Could it be a picture of one of the patrons, the Baroncelli family, who paid for this to be made? We don't know, but that is a conscious decision to break the symmetry. And there's an old Japanese proverb that says, if you want to break the rules of symmetry, you must first understand them. And I hope that today I've given you some of that understanding. So I will stop there. Thank you.
Thank you so much, Professor Hart. I've got a couple of questions from the online audience, and then we'll go into the room. The first question is, can you say something about 4-dimensional regular hypersolids?
Oh, well, I can. Yes, you were going to ask me how many there are, and I can't remember. But you can do that. You can do exactly the same kind of analysis and work out. So a hypersolid, if you like, just as you can make a cube by taking a square and dragging it along, and that becomes a cube. You can do that same thing going up a dimension, and you can take a cube and drag it along in a mysterious 4th dimension, and then join all of those things together, and that will give you a hypercube, so-called. So you can, and a regular example of that would have all of its 3-dimensional faces being identical to each other and the same. So you can do this kind of analysis, but yes, I don't remember right now how many of those there are. Homework.
I've got a question here about Neolithic balls. Now, I have a feeling you may already have answered this, so I'll ask anyway.
Okay.
Were there any with blobs which did not correspond to the numbers of vertices or faces on a polyhedron?
Yes, lots of them. Like about half of them had 6 blobs on them, and so those could be cubes or octahedra. But then very few of the others actually corresponded to known numbers of vertices or faces on Platonic solids. So that's where I think it starts to fall down, because you get ones with 135 blobs, and then what's that? So I think there are lots and lots of them that don't correspond.
I'm sure you're doing research into geometry. Can you explain what is the nature of your geometrical research? So
I would say the best encapsulation of my research area is the group theory that we've been talking about, which has lots of geometric applications, and the study of symmetry is involved in that. So my favourite thing at the moment is that I'm trying to understand, with numbers, you can take square roots of numbers and cube roots of numbers, right? And decide whether or not they exist or not. I want to understand whether you can do that in the more general setting of a group. So you can do it with, 4 is a whole number that has a square root, has a positive square root 2, and another one -2. We can conceive of that idea in the more general setup of these things called groups. And what does that mean, and how can we understand it? What does it mean to have a cube root of a symmetry, for example? Is that possible? So I'm trying to understand that at the moment, and that's this week's favourite item of research.
Thank you so much, Professor Hart. I'm afraid we're going to have to end there, but I just want to draw your attention to the next lecture, which on the 7th of February. Thanks so much for coming.
Thank you.